Later I will distribute the test one marking. But, Chapter 7, we learn about how to make our metal become strong. So we'll do solid solution, annealing, precipitation, and recovery. Right. So this is also one of the focus for your test 2. Now, the first thing is we use a solid solution to turn our material. Alright. So this one you read lah. So what I mean by solid? Mix something in a solid state. Example, like we have substitution, means we find a similar shape or radius that meet the Ohm's RH law, right? The Ohm's law. Then we the one you see on the screen here with the green color sphere. Or another method is interstitial, right? Interstitial, right? So we have learned about BCC, FCC, HCP, and you should able to find the gap that is inside the crystal structure. Then you should able to find either substitution or interstitial. Right. So this one, I want to highlight what is solute, what is solvent, right? So you'll be seeing solute and solvent wording in the test 2 and final exam. Okay, so you should able to identify which one is a solvent and which one is solute, because one of the question will ask you about the concentration, calculate the concentration. So if you are unable to identify which one is solute, what is solvent, then you might not able to score high in that particular question. Right. Okay. So the principle behind we do substitution and interstitial is to block the movement, right? To block the movement of the host from the stress. For example, you press force from the left to right. So when you press here, there's something here. So it's very hard to move in this area. Same with here. So you press from left, the orange color area, also very hard to move. Okay, so that is a principle or the reason how we make our metal stronger. Okay, there are two methods: substitutional by or impurity atoms. So you substitute again is follow the Ohm's law, the RH law, and this one interstitial. We need to calculate the space between the holes here. Okay. Now, one of the way is increasing the concentration of impurity, right? So when you increase the impurity, the concentration of impurity, meaning you add the green color or the orange color inside the solvent. So when you increase your solute concentration, you're going to increase the density of the material, and it will make the material stronger. So for example, so if you add in impurity, it will increase the tensile and yield strength. So we already cover chapter 6, which is in material strength, material properties, and also it is one of the question in your test 1, right? So as you can see here, the left-hand side is the tensile strength, and the x-axis is nickel content, which is in weight percentage. So we have learned this one in either chapter 3 or chapter 4, when we learn about concentration. There are two types of concentration. One is AT, which is atomic weight, and then is a mass weight percent. So as you can see, the blue curve here is that if you increase the nickel, especially when you use the stainless steel, they use a lot of nickel, right? So if you increase the nickel, you increase the tensile strength. Same with here, right? So this is yield strength. Yield strength also increase when you increase the nickel content. And the elongation. If you increase the nickel content, elongation reduce. Okay, elongation reduce. Why? Because there is not enough space for the holes to move. So it's very hard to elongate because you already add in the impurity inside the solvent. Okay, so these are the three graphs which is important when you explain about the strengthening mechanism. All right, so this is the one, nickel content. You increase the nickel content. You link elongation with ductility. Elongation with ductility. So this one is more into the microscopic dimension. So you add impurity atoms inside the crystal structure. So for example, this one. So if you add something that is small size than the host or the solvent, so when you have a force acting on the object, everything will squeeze in, right? Everything will squeeze in, right? The orange color arrow. So we call it lattice strain. Okay, lattice strain. Again, what is lattice strain? What is lattice stress? Don't confuse between strain and stress. Stress is force divided by area, and it must be perpendicular to the area. Strain is a deformation, which is L over LO or D over D or area. Okay, so strain you have two. One is lateral direction. One is a longitudinal direction. You have two. You combine these two, you get a ratio. You get Poisson ratio. Okay, so here, about lattice strain. Lattice strain is a deformation of the shape of the cubic, the crystal structure. Okay, so these are the explanation why when you add a certain material, what happened to the metals. So how the strengthening works is because the dislocation movement is restricted. So these are the keyword when we look when we give you a test or question to explain the strengthening mechanism. The highlight word that this dislocation movement is restricted is one of the answer that we're looking for. Okay, so you need to explain why you can strengthen the materials. Let's say you add nickel just now. You add nickel, what happened? So it's because of the dislocation movement is restricted. Okay. So this one, impurity atoms that is smaller than a host. So if you look at these orange color atoms, it's smaller than a host. So there's a space there. So when you squeeze the metals or you have a force on the metals, right? So there's a deformation happen. So when the deformation happen, tensile means there is a pulling of the surrounding things. Tensile strain means a deformation because of the tensile loading. You are pulling the materials. So you're able to pull the side material together. So you are having a tensile strength. Okay. So opposite of this case is not tensile, but compressive strain. What I mean by compressive strain? When you have an object which is bigger than the host or solvent. Okay. Now, RH rules tell that you should able to contain the size of the radius within 15% of the host. So there are two cases. If it is positive R, 15%, here, 15% R, so it means it's bigger than the host. So you're going to push the material. So you're going to compress. Okay? You're going to compress the surrounding host or sphere. So it becomes compressive strain. When it becomes negative, it becomes tensile strain. It is how you explain when it becomes how you restrict how you restrict the movement. It's because there's a space there or there is a lack of space. If it's loss of space, then it becomes tensile strain, deformation. You pull the material around. But if the orange color sphere is bigger than the surrounding, then it pushing the boundaries. When you push, it become compress all the surrounding host. So it become compressive strain, okay, or compressed strain. So, okay, so this is the one that I draw on the whiteboard just now. So you should able to identify what cases is left-hand side, what cases is the green color cases. Okay, so this is quite direct lah. Okay, quite direct. Okay, so here, for the solid solution strengthening, again, we have two cases or two mechanisms. One is through substitution, means we remove, not remove lah, but we find a space or a impurity that's the same size with the host or solvent. Okay, so but again, if you're following the Holmes rule or RS rules, you can either be less 15% or bigger 15%. So if you less than 50%, mean you have a loss of space, it becomes tensile strain. If it's bigger than the host, then it becomes compressive strain. Okay. So this one you read lah. You read. Okay. Okay. So another one is the dislocation. Previously, we learned about edge dislocation, which is there's a missing particles or missing sphere at a certain area. Then we draw a T, inverted T. So it means that there's a stopping. In this case, this is the very healthy side. So up to this side, there is no more normal particles here. So there's an inverted T there. And in the edge dislocation, you can put in a smaller substitution impurity to the slip plane, okay, to stop the movement. Again, the strengthening mechanism in the metals, usually the keyword there is restrict the movement. Restrict the movement of the atoms. Okay. So this is also the same. Okay. So again, we'll keep repeating resistant to, oops. Okay, resistant to slip is greater or something lah. This one you also read, but again, it's just to restrict. The keyword here is restrict the movement. Okay. Okay. So two important factor in solid solution strengthening. Again, solid solution strengthening, there are two ways. Either substitution, you substitute the green color ball, or you put in impurity, like in this case, orange color impurity, very, very small. If it's fit inside the gap here, we call it interstitial impurity. Okay, the first one is relative size factor. So you want to do strengthening, you need to look at the size of the atoms, right? The R, the radius. So again, dislocation movement, you want to restrict the movement by using size. Size. Second, the short range order. Short range order here is okay. Short range order. This one is when we study polymer. You know polymer. Polymer consists of monomer. You join the monomer together, it becomes polymer. Okay, like a rubber lah, rubber. Okay, so you want to disturb the movement, you add in a shorter range of order, means you put in small monomer there. So when you put in monomer there, you will restrict the things. So the second one, short range order, this one is normally in the polymer object. Okay. Right. So there are two factors. One is relative size. The other one is the sort range order. Okay. Just now, before this, is more on the molecular dimension. Means we add in impurity. That is the first method lah. Impurity you add in. Second one, we go into the second method already. It's called strain hardening. Strain hardening, you make a ductile metal. Ductile is like rubber, bubble gum. It becomes harder and harder. So how? By plastic deformation. Okay, or we call it work hardening. Right. So strain hardening, it will be like if you're familiar with the bread. You make bread, you like roti canai, you roll the things, right? So when you roll, in metals, of course, when you're making bread, it becomes softer and softer. But in bread, in metals, when you roll it more and more, it becomes harder and harder. That is the behavior of metals. Okay, so strain hardening is like making bread, but this one is you roll on the things, right? So it's called co-working. You make deformation on the metals itself by pressing, by rolling, and so on. So it's called co-working. Again, co-working is at take place co-relative to the melting temperature. So it is mean as a co-working. So co-working is referring to the melting temperature, EM, melt temperature. So as long as the working temperature less than the T melt, then it becomes co-working. If the temperature is more than the T melt or very, very near to the T melt, it becomes hot working. Okay. Then we have one equation for today. It's called percentage of co-working. Percentage of co-working. Take area divided by change of area divided by 100%. Okay. You look back. You look back at the recording. Okay. So we actually half of the chapter already, and this one will come out in your test too. All right. So we calculate percentage of co-work by using the change of area to the area. So this one, if you co-work means you can pull, you can roll it, and so on. So this is the equation, the equation for that one. So there are a few graphs that very popular for assessment. So in here, the first graph here, y-axis, the yield strength versus percentage of co-work. So just now we done one equation, percentage of co-work is a change of area divided by original area times 100%. Basically, it's a deformation or it's a strain. It's a strain equation. So here, as you can see here, you have three different lines here. You have steel, brass, and copper. So you have red color, orange color, and blue color. Okay, so let's look at the percentage of co-work. So if the percentage of co-work increase, you see there's an exponential behavior, but the yield strength becomes smaller and smaller. The change of yield strength becomes smaller and smaller. Okay, same with here. Here is the tensile strength. So the percentage of co-work, tensile strength also change, right? And here is ductility. So for chapter 7, you have three kind of main properties. One is yield strength, one is tensile strength, one is ductility. Okay, I repeat. There are three main important parameters in chapter 7: yield strength, tensile strength, and ductility. Okay, I repeat one more time: yield strength, tensile strength, and ductility. Okay. What is the main three important parameter in this chapter? I'm non-care. What is the main three main parameter? Yeah, I know you know. I asked them. The answer is on the screen. Later, I'm going to distribute your test one marks. Okay. Some of you did very well. Some of you did very bad. Right. Okay. So pay attention. If you still not understand what is yield strength, you still don't understand what is tensile strength, what is ductility, then you need to go back to chapter 6. Okay. All right. So this is percentage of influence of percentage of co-work. So 0%, 4%, and 24%. You see the stress also different. Okay. So it means if you have more co-work, it's able to handle more stress, right? Okay, so it's like making a roti. So the more you roll it, or you strengthen it, or you co-work it, then it becomes stronger and stronger, right? So when you become harder and harder, ductility will reduce. So this will be this third graph will be the killer question. You'll be confused with tensile strength and yield strength. They will show one student fail here. You don't understand why strengthening ductility reduce. So if you miss this one, review back or listen back to the recording. Right. So this graph is more on the why we need to do strengthening, or how do we do strengthening. So in the industry, how you do the strengthening, you pull the metals, you let go. So here you pull the metals, then you let go, you unload it, unload your force, then you apply the load again. It's called pre-stress. So if you're in the civil industry, you learn about pre-stress structure. So why they have a pre-stress structure? Because when you pre-stress it, it makes the structure stronger because of this strengthening mechanism. Okay. Right. So this one is a self-explainer. Okay, self-explain. All right. So let's say we consider 70% copper and zinc. Okay. So copper and zinc. Copper, look at this color. Zinc, look at this color. Okay. So if you are given this graph in the test, so this one, I should give you the legend for what is blue and white. Okay. So if you're this one is what? Percentage of co-work strength, employed oxygen-free copper. So this one is copper. This side is the 70% copper and zinc. Okay. So you can see this one is the pure copper properties. This one with 70% copper and additional of alloy element or strengthening element, 30% zinc. Okay, so again, now you start to see the weight percentage. Okay, so this one already covered in chapter 3 or chapter 4. So if you haven't familiar, please go and review the chapter. So I pick one. For example, you see the tensile strength. Tensile strength, if it's a pure one, minimum you'll get 30. This one is in KSI, kilo square inch. But anyway, we just qualitatively look at the numbers. So if you look at the blue color, you start with 30. But here, if you mix with 30% of zinc, you have impurity inside the material, then you'll see it will start from 30 something plus, and you add impurity, it will increase more than 30. Just now on the left is 30 something over here. But if you increase the impurity, you will increase to 40 something, very near to 50. Okay, so this is the tensile strength, and elongation also same. Okay, so elongation, pure metals or pure copper in this case, you see it's about 25%. That's 25. The yield strength, the tensile strength here is about KSI. So it's about 28 something. But you see here the elongation, the strength increase up to here is about 20 something, here up to 70. When you add impurity, 30% zinc. And then also the percentage of co-work also, you see, you will flatten the curve. Okay, you will flatten the curve. And so on. The rest you compare side by side. Okay. All right. So this one you read. It's basically explain what this is. Okay, so how will your test look like, or final exam look like? So you'll be seeing something like this, a very, very short paragraph, ask you to calculate something. So you calculate the tensile strength ductility of a cylindrical copper rod if its co-work in such a diameter reduced from 15.2 mm to 12 mm. What is the percentage of co-work? Can you calculate the percentage of co-work? What is the answer? What is the answer? Can you press calculator and calculate? $19.4, 19.7. Agree? Other guys, please verify this answer. Okay, so you put in all the numbers, pi r square or pi d square divided by 4. Okay, right. This is also one of the area where some students they score very low marks. They thought they know, but when they substitute value, okay. So first, when you answer question, write the formula. Okay. So as you can see later, when I distribute your test one, you will see. So why I score very low? Because you don't write general equation. Okay. And your general equation, you also do not agree with the question. Some question I already give you some parameter, but you substitute the wrong one. Okay. Okay, so we get 35%, about 36%. So we go back to the curve. You will see appendix graph in chapter 7 question. So you need to smart enough to choose which curve to use. So first, you might calculate the wrong one. Okay, so let's say the first part, just now you say 19 point something percent. First part you calculate wrong, second part I don't need to mark already, sure wrong. Okay, so check your answer always. So here you calculate is 35.6%. The question asks you tensile strength and ductility. Okay, we look at ductility first. This is the ductility graph. What is the material? Copper. There are 3 lines here: brass, steel, and copper. So you go to 35.6%. about here, about 36%, about here. You move up, intersect, go to the right, is about 8 or 7%. Okay. So in the test or final exam, we will adjust the graph according to the ruler scale. I hope you understand what I mean. We will adjust the graph when you put your ruler there. Let's say it were like 8 cm or 8 mm. You need to convert scale down accordingly. No. So let's say the graph here to here, let's say 0 to 10. Here is 8 mm. You put your ruler there, you'll see 8 mm or 12 mm, something. So let's say this case is arrived here. You need to convert 8 mm. This you need to measure lah. 8 mm equal to 10% ductility. Here you get an X here. So X mm equal what? You need to do interpolation. Yeah. You don't guess. You guess, you get a wrong answer. You need to scale. No, you'll be given a graph, but you can use your ruler to measure it. Okay. So bring ruler for your test. Yeah. No, you won't get 10 one. I won't be easy one. That question. Lesson 8 lah. 8 equal to 10%. It's the one that you arrive lah. Like here, 35.6. So it's about here. You arrive here. You'll see this arrow. Then you measure lah. Yeah, you use your ruler measure. What is the length here? Yeah. So let's say it's 6 mm. Of course, you will be given. Yeah. So you need to detach the graph and then stapler with the answer. Okay. So you need to find how many percent. Okay, this one from graph. Okay, this one from graph. So same, don't read the wrong graph. Here you have tensile strength, you have yield strength. Answer, the question asks you tensile strength. Don't read the two. And don't go and do another one and ask me to choose for you. If you go and do 3 steps and ask me to choose, I'll choose the wrong one. Okay, I will purposely choose the wrong one. So don't make me, don't make your marker to choose for you. Okay. Right. So here we use a center graph, same also, 36% copper. Go here, so it's about 300 something. Okay. So this one is quite direct. It's nothing complex. Here, this is example 1. It can become a design problem like what you see in your test 1, question 2. Okay, so means that the customers give you something. Then let's say the customer give you a ductility percentage. Section A. Customer give you a spec. Then from there, you get a range of the percentage of co-work. Percentage of co-work, you link to here and here. You decide what is the percentage of co-work. For example, the question will go like that usually. We will give you the percentage of ductility that restrict your ductility. Then come here, you get 1% here. So then it will tell you, it give you another one like question B. It will give you your tensile strength must maintain within 400 and 300. What is the percentage of co-work that you need to do in your operation? Means here, you reverse, means you do the same. Like for example, the question, I think I have one question, example question in this chapter, but later lah. So this one, we already done with the graph. Then the second one is on the recrystallization. This one usually come out in the test 2 lah, test 2. So what we expect you is to draw this graph, this figure. Okay. Now, when you do this recrystallization of plastic deformed metals, when you roll the metals or you do something on the metals, there are three phases. One, recovery, recrystallization, and grain growth. What mean by recovery? Recovery means you roll it and you know that metal can go back its original shape when it's elastic, right? So the graph, tensile graph, stress and strain, you have a straight line here. This is elastic region. Then it will curve. This one is plastic region. So when the first phase is called recovery. So recovery, you draw something strain here, a strain here. Then recrystallization, you start to recrystallization means you see a new grain inside the metals already. Okay. Then after that, you continue to roll, it become here. After the plastic region here, then it become more and more grain. The grain become bigger and bigger. The grain, the small grain here, become bigger and bigger. Okay. So on the top here, the bottom one, you break your graph or your picture into three regions. One, recovery, recrystallization, and grain growth. There are three reasons. Then on the top here, you draw this diagram. Then on the top here, you draw strength and ductility, hardness. Then this one is the internal residual stress. Internal residual. What I mean by internal residuals means if you roll on the metal surface, you have a stress inside there. Okay, so it will reduce, it will stabilize when you have a new grain growth inside there. Okay, then you see the ductility increase, then is fade off. Hardness also, hardness start from very high, then it become flat like that. Strength also like that. Okay. So this is the effect of annealing. Annealing means you heat treatment, you heat up the metals, right? So new terms for today lecture, annealing. Annealing is you do heat treatment, you reheat the metals. Okay, all right. So this is a cold rolling, a cold road. So this is a cold road means you put in the metals through a roller and it pressing on the metals. So when you're pressing, you are strengthening the metals. So you see the microstructure become more and more dense here when you roll it. Okay. So when you roll it, when you have a defect or you have a space or void there, you squeeze the metal particles together, you actually eliminate the space. All right. Okay. So here, when you do cold work, when you do cold work, you're actually reducing the gap of void. Okay. So this is under microstructure. You see there's a straight line, means you elongate in the rolling direction. You roll it, it's like a layer cake. You do layer cakes. Okay. Then this one is under magnification. You have a loss of network start to grow already. Okay. Recovery. So what is important for recovery is that the range is just below the recrystallization temperature. So today your temperature have one range. One is below recrystallization, means there's the new, before there's a temperature that the new grain can grow. Right? Okay. So this one you read lah. So recrystallization, you will see small crystal grow from from the left to right diagram. So here you see a new grain start growing, like the one you see here. And how do you see this black grain, this black color? You do etching. You use chemical to do etching, right? Okay. This one also you read. What is recrystallization? Recrystallization is a formation of new set of strain-free and equaxial grains. Okay. So once you grow the grain, it will go into a full grain. Okay, become bigger and bigger. The black one become bigger and bigger. Okay, so there are two mechanisms how recrystallization happen. One, isolated nucleus can expand with deformed grain. Isolated nucleus can expand. So it means inside here, they find a space and then the new grain grow there, it will expand. Second, high-angled grain boundaries can migrate into a highly deformed region of the metals. So this one is grow. Second one is find a high-angled grain boundary, means there's a space there for it to slot in. Right? Let's say there's a space there. So let's say there's a grain over here. So it will expand and squeeze inside the canyon here. Okay, there are two mechanisms. Okay. So when there's a growth of new grain, that's why the tensile strength decrease. Okay. And ductility increased by annealing treatment. They cause the structure to be recrystallized. Okay. So this is changing the properties when you do heat treatment. So tensile strength will reduce. Tensile strength will reduce during the recrystallization stage. Right? So this example example for 50% cold road, tensile strength and elongation. The left is tensile strength, right is elongation. Right? This one also you read lah. Okay, so this is more colorful diagram. So still here we have three phrases: recovery, recrystallization, and grain growth. So what is important for this graph is you know that there's three phases: recovery, recrystallization, and grain growth. What happened to ductility? Ductility will increase, tensile strength will drop during this one. And this table is important when the question asks you about recrystallization and melting temperature. So this one you can refer. Always read the unit SI, which is Celsius, not Fahrenheit. Huh? This one? Of course, Celsius. Celsius. If you go to US, then they use Fahrenheit. Okay. Right. So this is the apparatus, how they do. Okay. So just give you an idea what is the recrystallization happening in animation. So what is annealing? Annealing is heat treatment. They will go through a furnace. The furnace increase the temperature. So the metal go through, heat it up. Then the three phases will happen. So the grain structure will start to grow. So these are the few factors that can affect this process. Okay. So this process, recrystallization, they increase the ductility, they drop the tensile stress. So it depends on deformation that you want. The customer want how many % of deformation, temperature, time, initial grain size, and composition of the metals. Here, composition is percentage of WT or AT. This one. Okay. So this one also you read how recrystallization happen. Okay. So if you want to make the recrystallization to be happen, make sure there's a minimum amount of deformation inside the metals. Right? Smaller degree of deformation, the higher the temperature needed to cause recrystallization. Right? And so on. So you read. So this is plotted time versus inverted T for aluminium. Okay, this one you also read lah. There's a certain process for recrystallization, right? So this one normally happen. I will ask you in the test 2, question 2, on describe how recrystallization process happen. You need to mention this 5 point plus this diagram. Yes. Okay. 6 steps. Okay. So this one. Which one? Of course, this is the most important thing. I won't be so detailed, but what's important, you have 3 phrases: recovery, recrystallization, and yeah, I mean you write 3 phrases: recovery, recrystallization, and grain growth. Blue line only. Important is this one. You need to draw a line here. So this one, co-work and recovered. So this one you need to draw a grain, then point to that. As long as you draw something or you can make a small dot, black color one also can. Then you draw, then you write new grain. Okay. No, you draw like something like this like three region. So the one is like you use this one usually you don't need, but it's good to memorize. This one is qualitative, means you know that when you move towards the right hand side, the more you increase the temperature, ductility will increase. You increase the temperature, like you melt, like you are melting the metal, right? So ductility will increase on. Right, you melt the things, so the strength also will drop. Okay, so this is a qualitative representation, not the exact value. Right. So what is important is you draw the new grain, and then here is the big grain. Is a bigger grain like that. Okay. So on the left is like a flat line here. Then you add in some grain, but this one becomes smaller and smaller. Then this one smaller become bigger and bigger, like a scale, fish scale. Okay. The factor here is this word. You increase temperature. Yeah. It's bendable means ductility improve. It will break, but is the resistance to breaking is harder. Means it's able to pull. Then the strength will drop. The hardness will drop. Strength will also drop. Means it's more easier. You can pull, but it cannot handle high stress. Okay. It's like bubble gum. You can pull with a very less force. Okay. So this will be the the question, right? So question 2, it gives you, if it takes certain minutes to recrystallize a piece of copper at 88 degrees C and 200 minutes at 135 degrees C, what is the activation energy of the process, assuming process obey Arrhenius equation, give you by this one, and the time of recrystallization is so and so, right? So you convert all the parameter, the time, because the question then didn't force you to use anything, either second or minutes. So I would highly recommend you always convert to unit SI. But this question doesn't mention anything. And for engineering material, your parameter is not, I mean, your constant normally is not related to second, right? Usually related to Kelvin. That's more important. So temperature to Kelvin. Then you use the equation over here. Okay. So you have two equations. T1 equal to CE exponential this one. Okay. Actually, yeah, this seen this one in the previous chapter. It's called Arrhenius rate equation, right? So T for the first case is 9 10 power 3 minutes equal to CRQ, the temperature 361, 88 degree to 361 Kelvin. You do the same for the second case where it increased to 200 minutes and the temperature become 135, it is 408 Kelvin. Then you divide the equation. When you divide the equation, you become a ratio, right? And exponential ratio is a minus. You take this one, divide this one, when it's a ratio. Exponential one is a minus. Okay. So you take this one, divide this one, you get 45. This one, divide this one, you get. What is R? R is a Rankine constant. Rankine constant, okay? You can find in chapter 5 or chapter 4, I forget already. Okay, inside the slides have. It's a constant value, right? It's a constant value. Okay, so then you, because you are seeing the exponential E, you need to put it into ln, both sides. Okay, ln 45, and then you pull the exponential, become a constant value. So you get your Q. Q. So this example 12 is actually to recall what is a Arrhenius rate of equation. And then when you see these two scenarios, how you solve it, you just find the ratio, then you find the unknown, right? Now, most of the part, student, you start here. You don't know how to proceed here when you see exponential. Okay, remember to use ln to solve question. So another one. Okay, so this one is recall what you learned 5 minutes ago. So cylindrical rod, non-coated work brass, now having initial diameter 0.6 mm, is to be cold work by drawing such a cross-section area is reduced. Now it required to have cold work yield strength at least 345 megapascal. Ductility in excess of 20% elongation. In addition, a final diameter 0.1 is necessary. Describe the manner of which this procedure may be carried out. Means you need to use the tree graph that you see just now. Then you need to establish a work order. Means like, first step, operator need to do what? Second step, operator need to do what? Like step 1 do what? Step 2 do what? Step 3 do what? You need to explain. Okay. Okay, so basically you derive your step through the graph. Okay. Again, this kind of question is chapter 7, only one equation so far. We did this one. Okay, percentage of cover equal to the ratio of your deformation in terms of area. Okay, times 100%. So here, you need to find the percentile of co-work that you need. So you change from initial to another one, okay? So it tells you final diameter is 5.1 mm, okay? 5.1 mm. So here what is missing? The percentage of co-work you don't, you can, okay? So you find percentage, so 64, 6.4 and 5.1. You know that from the beginning to the end, how many percent of co-work you need? Okay, you substitute value, you find about 36%, 36.5%, right? Again, reminder for this module, a minimum 2 decimal place, maximum 3 decimal place. Right? Okay, you find the percentage of co-work, you go to the tree graph there. Okay, then what information you need, you have is that it gives you, customer requests you to give products at least 345 megapascal. The left graph gives you yield strength. So 345 is about, sorry, 36%. If you refer to co-work, it gives you how many percent? Brass, right? Go up there, go to the left, the yield strength become what? About more than 400. The question use brass. So read carefully lah. So the first thing that you calculate the percent of co-work, in this case, you know that it's about 37%. So, no, first one is not cannot. The customer need what? So you get 400, can or not? Can. Because the customer say you need minimum this one, but if you do 36% or 36.5%, you get more than 400. So it's actually the first test already passed already. It means if you do 36.5% co-work, your yield strength pass. Okay. Then second one, ductility excess 20%. This graph, right? So 36% about here, brass is about here. Does it pass? Yeah. Okay, so this one, tensile strength, does it give you tensile strength? Okay, tensile strength. This one is quite kind this question, but normally when come to test 2 or final exam, you need to use the tree graph, right? This tree graph, right? So this one is just a cross check. Like if you do 36.5%, the tensile strength will reach 500. This one, ductility, if you do 36.5%, you extend to the left, it's less than 10%, which is not the customer one. You need 20%. The customer want you to give a product that can able to give ductility more than 20%. So if you do co-work this one, you cannot meet customer one. Understand? Or means the product may be installed on the spacecraft or on the very high-tech machine, but it cannot. If you do this percentage of co-work, you cannot. So you need to propose to the customers. What is your proposal? Customer say that final diameter, this one is necessary. So what can you do? This is think outside the box one kind of question. Initial diameter, 6.4 mm. You need to give the customer, when you send the products, the customer want to see 5.1 mm. This is what customer will fix already. When you deliver this one, the strength, the tensile strength, need to be more than 345 megapascal. Ductility need to more than 20%. This is what customer want. He doesn't care what is your process. So what can you change? No, cannot. Customer want to use brass. Okay. You get the correct answer. Change initial diameter means you buy a supplier that give you the raw material in the, but what is the size that you need? You need to calculate lah by using the percentage of co-work. So from the graph, you need to decide. You need 20% ductility, right? So how many co-work you need? Here. You go here, extend here, go down. How many percent? About 25, right? Okay. So it's about 25% co-work to meet this requirement. Initial customer proposed, you calculate 36.5%. Okay, 35%, the one that you see on the slide here, it passed the yield strength. This one you don't know. So you know that minimum you need 25%. Can you do something on the graph? This one. What is the yield strength when you only do 25%? About 25% lah. No lah, no 25 lah. 20. Not 25 lah. It's about 20. About 20. Less than 25 lah, like 21, 22%, right? But you can check on the graph. So here you draw the steps that we expect you that you go here, you draw an arrow, you drop down, you get 1% here. Then you transfer this percentage to this graph, 20 something. You draw up, push to the left, you get something 380 lah, about there. Right? About 3, you pass this value, can, right? So what you expect is you draw arrow from 20, drop down, you get value. Transfer this value over here, draw arrow up, draw to the left, write the number here. What do you see? Okay. Then you propose to the customers, or not propose lah, but you tell your production floor, don't use this one. Use diameter by using this equation. Okay. You know your co-work already. Now about 21 to 22%. You can find value of this one. Right? So you know your final area. Right? So this is area final minus area initial. Area initial. Can find the missing parameter. This one you know already. Okay. Initial. Initial, final. Okay, initial, final. So same lah, actually same lah. Okay, so you have one unknown here. Then you have this one. Customer one final 5.1. You have this one. You have this number. You can solve. Okay, so second one. What you mean second one? This one. The question didn't ask you tensile strength. Didn't give you, but in the test or final exam you'll see. You'll see that. So here, yeah. It's the same concept. Actually, you arrive at the same answer. So, but it's more safe that you check, in this case, you check the ductility first, reverse back to yield strength. Rather from yield strength, you check back here. Okay. So you see the purple color is the step that we mentioned just now. So what you do, the deformation must be between like this one, the 345, like what you say just now, 345, you drop down, you get 20%. So you get a range from 20 to 23% of cold work. Okay. So you need to choose one value. Okay, you need to choose one value. So what is the minimum size that you need to order from your supplier? Right. So you need to tell your QC, hey, when you import this one, you cannot too big or cannot too small. Right. So take average 21.1, 21.5% cold work. So you'll find the answer is 5.8 mm. So you change the initial 6.4 to 5.8 before the cold work start lah. Okay, so these steps is find average, but the kind of question will be in your test 2 or final exam. You need to find the range of diameter of your initial, this one. Okay. So with this, we conclude chapter 7. Okay. So these are the type of the question that might be coming out. Okay, with this, we conclude chapter 7.